The Channel, the natural barrier between Great Britain and Europe. Throughout history it has provided protection, but has also hindered trade and transport. Since the middle of the 19th century, men have considered ways of forming a permanent link to the mainland of Europe. Others have considered any permanent link a threat to the security of the island kingdom. In 1875, the first survey of the Channel seabed was made, led by 3 French engineers. Of 7,700 attempts at recovering samples of the seabed, rather less than half were recovered. The geological map made from these samples showed the possibility of driving a bored tunnel under the channel. In 1881, pilot tunnels were started from each side of the channel for a distance of about a mile. A boring machine designed by a Colonel Beaumont was used. Both tunnels confirmed that tunneling was both quick and safe in the lower part of the lower chalk. The venture was short-lived, mainly due to Sir Garnet Wolseley's fear of such a tunnel being used for an invasion. The idea of a link was kept alive by a few far-sighted people and their successors. So, in 1957, the British and French Channel Tunnel Companies joined the Suez Canal Company and Technical Studies Incorporated of America to form a Channel Tunnel Study Group. There are 3 possible ways of forming a permanent link: a bridge, an immersed tube tunnel, or a bored tunnel. The group carried out a preliminary site investigation, and based on the group's engineering consultants, French, British, and American, carried out a feasibility study and an estimate for all 3 types of link. In 1963, the British and Ministers of Transport published their conclusions based on these and various other proposals. In 1964, the British and French governments placed a contract with the study group to carry out a detailed survey of the Channel seabed for a possible immersed or bored tunnel link. The group set up their headquarters in Dover Castle, manned by a joint Franco-British staff with another office in Calais. The most advanced scientific equipment was used, but it was vital that the results from these should be plotted accurately. To do this, the position of every type of geological or geophysical observation carried out was determined, either by Decca Hyfix or some other means. The main Decca station was set up at St. Margaret's Bay, with slave stations at Dungeness. The equipment installed in the caravan and at Cap Blanc-Nez. The system employs 2 intersecting patterns of lines, known as the red and the green, produced by the interference between waves from the master and one slave station. They are received on the ship, and the position can be read off digital counters and plotted on the chart. A track reader can also be employed where a predetermined line is plotted, and the pointer shows the ship's deviation from the proposed course. The position given by Decca Hyfix was accurate up to approximately 6 feet. For surveying the exact position of the boreholes, hydrodists or theodolites were employed. The hydrodists give corrected distance readings, read off as the dot on the circle. This was found useful in bad visibility when the theodolite could not be used. Both the hydrodists and the theodolites could give accurate positioning to within a foot. The surveyors using hydrodists or theodolites, as well as those at the shore stations, were in constant radio contact with the ships.
Roger. Out.
Coupled with accurate positioning, precise water depths were required. At Dover Harbour, a new tide gauge with a continuous recorder and a protecting tube to damp out wave patterning was installed. The new tide gauge at Dover was used in conjunction with the existing Calais tide gauge to allow tides to be estimated at required points. Depth readings in the channel were taken by a direct method, such as sounding lead, and by echo sounding. For a geophysical survey of the strata below the seabed, the EGG system was used. This employed one of 2 different types of sonic pulse, produced by either the sparker, seen here being towed over the side and giving off a visible spark, the boomer, here resting on the afterdeck, which gives off a dull thud. The principle employed is similar to that of the echo sounder, except that the sonic pulse is reflected from the different sub-bottom strata, as well as from the seabed, and the reflections are received by a hydrophone towed on the opposite side of the boat. The results were plotted on a continuous recorder, designed so that a good picture of the sub-bottom strata could be built up. These results could then be related to the information obtained by drilling. The drilling was first undertaken at sea by tank landing craft, which were later supplemented by two drilling platforms, Gem 111 and Neptune, when they became available. The tank landing craft used included the French Coville and the English GW14, which are typical of the best type employed. The ships required 6 moorings each, with a 5 to 7 ton anchor, each of which had to be buoyed. The strong tides and bad weather often hampered the maneuvering of the vessel into its exact position. The ships were also required to have warning navigation buoys with flashing lights to comply with the international shipping regulations and more specific requests of Trinity House and Farze Balize. To handle the heavy mooring equipment, 2 ex-naval boom defense vessels were chartered. Each position was moored and buoyed in advance, so that the drilling vessel could take up its position with the shortest possible delay. Aboard GW14, the drilling was carried out down guide tubes that were assembled and driven into the seabed. Rotary hydraulic heads were used to turn the bits, which were tungsten carbide or diamond tipped, depending on the nature of the ground. The time-consuming factor in drilling is the assembly and recovery of the drilling rods, each one being held by a foot clamp while the previous one is unscrewed and stacked. With any rotary drilling, the drilling rods have to be stacked. On GW14, they were laid out in the well formerly used to carry tanks. When the bit was removed, the core was carefully extracted from the core barrel. The cores were then placed in core boxes, marked to show the top of the sample and the bottom, and from what depth they had been recovered. On board the Coville, a double-deck platform and a smaller diameter drill were employed. An alternative type of rotary head was used to drive the drill. Again, diamond and tungsten carbide bits were used. The cores were then taken to stores at Dover Castle or at Calais, and in both places, especially equipped laboratories were set up to carry out various tests on them. Samples for testing were cut from the cores at recorded intervals. They were then put through a series of routine tests for strength and quality and other more complex tests. For the determination of the fossil content, samples were taken at regular intervals. These were broken up, dried, treated with white spirit, and boiled to cause the sample to disintegrate. Then the samples were dried under special lamps, and after fine sieving, each specimen was labelled and placed in a test tube. The microfossils were then identified and counted under microscope. Comparison of certain ratios of microfossils established which zone of the various beds of lower chalk was present and the geological level in the borehole. A further series of calcium carbonate tests were carried out to establish the clay content. The clay content defines the extent of the chalk marl layer, where any proposed bored tunnel would be driven. Later in the survey, land borings were carried out in much the same way as those at sea, though under much easier conditions. These borings, 10 in England and 9 in France, were designed to investigate conditions along the approach tunnels. At these borings, subsidiary tests were carried out. A reference borehole was sunk in the calm of Dover Harbour, down to the greensand level. This borehole was used for extensive logging tests to act as control for similar tests at sea. A series of such tests were carried out by lowering sondes down the boreholes. These revealed on a continuous recorder some of the physical properties of the rock present. Permeability tests were carried out using several different forms of packer to form an impermeable seal in the borehole. Here, a double packer is lowered down a borehole, and each packer is then inflated with compressed air. A measurement of the loss of water, pumped at various pressures into the space sealed between the two packers, allowed the permeability of the rocks near the borehole to be determined. Two drilling platforms, Gem 111 and Neptune, were chartered later in the survey. The Gem 111 has tubular legs, which are raised while the platform is being towed by tugs into position. Then, pneumatic jacks lower the legs onto the seabed and lift the platform clear of the sea. The Neptune, on the other hand, has girder legs, which were operated on a rack and pinion system. Advantage was taken of using this highly sophisticated drilling platform before it took up its exploratory duties in the North Sea. Most stores and personnel were brought out by tender and hoisted aboard by catnet worked by the derrick. The drilling was a more elaborate version of the system employed by the landing craft. The rotation of the bit was of the normal oil well drilling type, using a rotary table and a kelly. The drilling platform had one particular advantage over the ships in that when they had jacked themselves out of the water, they were hardly affected by weather conditions. For the immersed tunnel project, samples of the seabed were taken by a sampling device. This open-ended weighted tube with a self-closing valve is allowed to fall onto the seabed. When hoisted aboard, the depth of sediment is measured by taking two measurements. One after the excess water has been drained off, and one after the sediment has been emptied into marked bags. The topmost stratum of the bedrock, where it is present, is removed for laboratory tests, careful note being made of the exact position. Also, for the immersed tunnel project, flow meters and samplers were used to determine the tidal currents above the seabed and the amount of siltation likely to take place in any dredged channel prior to the laying of an immersed tube. The model for the immersed tunnel route is distorted with a vertical scale 50 times that of the horizontal. So, although some slopes of the seabed appear steep, they are in fact relatively gentle, as a slope of 1 in 10 appears thus on the model. The immersed tunnel would be buried in a trench, but in the model it's shown by a vertical card resting on the seabed with true depths inscribed on the sides to the same vertical scale. The mean sea level is marked on the sides of the case. The different colours represent the different materials which outcrop on the sea bed. The model shows the considerable variations in depth up to 180 feet, so that an immersed tube would require about 14 changes of grade. The bored tunnel model was formed of vertical transparent sheets set at half-kilometre intervals and coloured to represent the geology at each profile. The positions of boreholes are shown by coloured rods. The sections are enclosed in a perspex case with a cover set above them to represent mean sea level. Owing to the extreme contrast between lengths and depth, the distortion is 1 to 10, so that a 1 in 10 slope appears considerably steeper than it actually is. The tunnel climbs from below Dover Harbour, passing under the 500-foot high South Downs, and emerges to the north of Folkestone, at the foot of the chalk escarpment. In the section offshore from Dover, the shape of an anticlinal fold is clearly shown, which makes it necessary for the tunnel to sweep to the north in order to keep well within the lower chalk. Towards the French coast, the strata are inclined quite steeply, and the tunnel line has to skirt closely along the upper surface of the Gault clay. It's here, at 24 kilometres from the British coast, that it will have to cross a fault, which can be seen in the sudden change of level of the surface of the Gault. After crossing the French coast, the tunnel divides with separate portals and has to pass through the upper levels of the chalk in order to emerge in a suitable area for the terminals. In this way, this most extensive and expensive survey for an engineering project was completed. 73 boreholes were sunk at sea and 1,000 kilometres of geophysical profiling carried out. This survey indicated that for either a bored or an immersed tunnel, no major obstacles such as large faults or buried channels will be encountered.